All right, so the final part of this chapter is Newton's law of gravitation. Newton's law of gravitation says all objects in the universe are attracted to each other. All objects in the universe are attracted to each other. And it's a gravitational force of attraction. Okay, so here I have two objects, M1, M2. M1 is purposely small, and M2 is purposely big. I picked this diagram on purpose to ask you guys a question. But look, is M1 an object? Yes. Is M2 an object? Yes. What does Newton's law of gravitation tell us? That these two objects will attract each other. There's going to be a force of attraction between these two objects. And then this force of attraction is a gravitational force of attraction. This force we're talking about is basically where gravity comes from, as you'll see as I keep explaining. Now, M1 and M2, different sizes. Are these two forces the same or different? M1 is little, M2 is big. The forces are still the same, even though M1 is small and M2 is big. Because look, what does Newton's third law tell us? You guys, you remember Newton's third law? Every force has a equal and opposite reaction force. So here's what's happening. M1 exerts a force on M2. That's this, right? This force right here, this is the force of M1 pulling on M2. Okay, so what does M2 do back to M1? It exerts a force. So these two masses are exerting force on each other, and those two forces are equal and opposite, right? Notice how they point in opposite directions, but they're the same force. Even though M1's small, M2's big. It's just like you sitting here in the room right now. Gravity is acting on you. Like the earth is pulling you down. The earth is an object, and you're an object. The earth is pulling you down. So what does that mean? You are pulling the earth up. You're a small mass, the earth is a big mass, but the force between you and the earth, the force on you by the earth, is the same as the force of you on the earth. Does that make sense? These forces are always equal and opposite. Okay, now, look, here's the equation for calculating the force of attraction between any two objects, M1 and M2. G is the gravitational constant. You don't have to memorize it. I'll give it to you on tests and quizzes. Don't memorize the gravitational constant, but you do have to memorize the equation. G M1 M2 over R squared. Okay, yo. No, they'll give you, on the AP test, they give you the constants, but not the equation. For the multiple choice, you have to have the equations memorized. Okay, so what was I going to say? All right, so let's say you have two small objects, like these two pens right here. So I'm holding two pens in my hand. Are these two pens attracted to each other? Yes. They are. However, you're never going to notice it. So here, Eric, hold those pens. Do you feel a force of attraction? No. Now, didn't we just say that all objects in the universe are attracted to each other? Yeah. So why don't we feel, if I have a pen here and a pen there, why aren't I feeling a force of attraction between these two objects? Well, it doesn't have to do with everything else. The masses are too small. So look, I want to point out, look at this gravitational constant. See the gravitational constant? It's right down here. This value right there. The gravitational constant, if you write it out, is 0.0000000. I think that's enough zeros. 6673. Dude, is that a big number or a small number? Incredibly small. Incredibly small. So, if you look at the equation, because G is so small, what must be true about the masses? One of them, not both, but at least one has to be big. One of these masses, now what do I mean by big? Do I mean like a car? Bigger. Do I mean like a building? bigger? A mountain? Bigger. I'm talking planet. You know, in order to get a noticeable force of attraction, one of these masses needs to be like on a planetary scale, like the Earth or the Moon or Jupiter, something really, really, really big. So now let's do this. So here's a pen. So let's say the pen is M1 and the Earth is M2. Is there a force between the pen and the Earth? Let's check it out. Yep, the pen, as you just saw, the pen got pulled to the Earth, right? There's a noticeable force there. Does that make sense? Okay, so the final thing I want to mention here, when you're using this equation, and this is super important, when you're using this equation, the distance, so R is the distance between M1 and M2, it has to be from center of M1 to center of M2. It's center to center. Okay? Now, there's two applications for Newton's law of gravitation. The first application is finding the acceleration of gravity above or on a very large mass, like a planet. So here's the Earth. So imagine you're standing on the Earth right here. Do we know what gravity is on the surface of the Earth? Yeah, on the surface of the Earth, gravity is 9.8. But what if you were like that guy, who is the Red Bull guy who jumped out of that, set the record for highest jump? Felix Baumgartner, yeah. So Felix got into some hot air balloon, and Felix took himself way, like I used to know how high he went, I forget. He went really high above the surface of the Earth. Is gravity up there still going to be 9.8? It's not 9.8. What happens to gravity as you leave the Earth? It goes down. So how could you find gravity at a height above the Earth if you knew the height? Like, so you'd have to know how high you were above the Earth. How would you go about doing this? Well, it involves Newton's law of gravitation. So let's say we're looking at Felix, right? Let me set this up here. Okay, so we're going to put Felix. Let me make some. So we stick this guy up here. We're going to call him M2. The Earth is M1. Okay, so is this guy up here, is he an object? Yes. Is the Earth an object? Yes. What do we know about all objects in the universe? They attract each other. So this is a gravitational force on Felix, the daredevil, and there's a gravitational force on the Earth. Okay? Now, if we focus on Felix, right? If we focus on Felix, look at, there are two equations that we now have for the force of gravity. What was the first equation that you learned for force of gravity? mg. That's still true. But look, guys, is g going to be 9.8 up there? It's not 9.8 anymore. It's an unknown. So mg, and is this m1 or m2g? m2, because we're focusing on Felix, right? Okay, what's our new equation for the force of gravity? gm1 m2 over r squared. So all we're saying here, all we're doing, we have two equations for gravitational force. We got two equations for gravitational force. Set those two equations equal to each other. What happens to m2? Cancels out, and we now have an equation for finding gravity where Felix jumped from. Okay? So which m is this? Is that Felix right there, or is that the Earth? It's the Earth. It's always the big guy. The little guy is going to cancel. Whatever the object is up there, it cancels out. And then remember, R is from center of Earth to Felix's belly button. But look, and I've had kids ask me this before, is the radius of Felix going to matter? You're talking like millions of meters, dude, from the center of the Earth up to where Felix jumped from. Okay, so that's probably what, like 8 million meters or something, plus another half a meter for Felix's belly button. You know, so the center to center, really the only things that's going to matter. I mean, the way you would have to do this, you take the radius of the Earth, because that's huge, and then you add the radius of the Earth to how high he jumped from. Does that make sense? So you got to figure out the total distance from the center of the Earth. You got it? Okay. Application number 2, and we're done. Okay, second application of Newton's law of gravitation is when you have one mass orbiting another mass, like a satellite around the Earth, or the Earth around the Sun. Guys, planetary motion is actually elliptical, but we're going to simplify things. In this class, we're going to go, yeah. Planetary motion, we'll just call it what? Circular. Even though it's elliptical, you know, an ellipse is just a smush circle. We're just going to keep things simple and pretend that planetary motion is circular. And that's endorsed by the College Board. They say it's fine. Planetary motion for this class is circular. It's a way to simplify things. So look, we have a satellite going around the Earth, right? So this right here shows the tangential velocity. If this satellite suddenly left the circular path, how would it leave the circular path? Tangent. Okay, but I'm going to erase this because I want to look at forces here. Not velocity, but let's look at force. Okay, let's call the satellite M2, and then the Earth is M1. So is the satellite an object? Yeah. So it's attracted to the Earth. Is the Earth an object? Yeah. So it's attracted to the satellite. And those are both gravitational forces. But let's focus on M2, right? Oh, and remember, for circular motion, make the center of the circle, which is right here, make the center of the circle positive. Why do we make the center of the circle positive for circular motion? What always points to the center? The acceleration. When an object is in a circular path, the acceleration is always to the center, so make the center positive. Okay? So focusing on M2 here, if we sum the forces, what's the only force on M2, on the satellite? The gravitational force, right? That's the only force acting on the satellite. What is the sum of the forces always equal to? ma. Now, what type of A is this? Centripetal, because the satellite is in a circular path. So now let's plug in our equations. What's the equation for gravitational force? G m1 m2 over r squared. Oh, by the way, what's this m right here? Is that m1 or m2? m2, because we're summing the forces for m2. Okay, so this is going to be equal to m2. Now, what's the equation for centripetal acceleration? V squared over r. Okay, so what drops out now? m2 cancels, and one of the r's. One of the r's. And you're left with v equals square root gm over r. So, what is this v right there? It's the tangential velocity of the satellite. Like the satellite's right here, boom. It's basically, you know, it's the speed of the satellite in meters per second. It's how fast the satellite's moving. Which m is that? It's the Earth. It's the big guy. And then r, again, r is always from center to center. The distance is center to center. And that's everything in Chapter 7. So next week we'll do problems. That's it.